All right, moving on to number 4. We have g of x is a function of x squared plus 1. And we want to find each of the following, all related to the derivative. So let's look at A. We want g prime of x. Okay, so this says take g prime and let your input be x. So g prime, this is for A, of x is equal to, well, it's just, here's g of x, so that's just the derivative of this. So we're going to take the derivative right here, which is f. It's almost a chain rule because this is the inside and this is the outside. So f prime, keep the inside the same. Then multiply it by the derivative of the inside, which is actually 2x. So you could rewrite it like 2x f prime of x squared plus 1. All right, number 1, or B, A. Option B. Now we want g prime of 2. Well, we have an equation for g prime of x, so we can just go ahead. So we already had g of x. We already have an equation for g of x. So really for this, g prime of x even. For this, we really just need to plug in 2 to the derivative. It's the derivative of g at 2. So let me plug in 2, and we've got 2 times, now all the x's become 2's, and it's f prime of 2 squared, so that's 4, plus 1. So we've got 2 times 2, which is 4, times f prime of 5. That would be the answer for part B. All right, part C. It's really similar to part B, except now they want us to take the derivative and evaluate it at x cubed. So once again, all these x's will now become x cubed. So we've got 2 times x cubed, f prime of x cubed squared plus 1. All right, don't forget your exponent rules here. F prime of, if you're squaring a cube, that means you multiply these. So it's x to the 6th plus 1. All right. Part D is where they kind of try to trick you, because a lot of people think that part C and part D are the same problem. Here, they want us to do something different. They want us to plug x cubed into g first, and then take the derivative, working from the inside out. So let's plug x cubed into g. So g of x cubed is going to be f of x cubed squared plus 1, which is really f of x to the 6th plus 1. Now they want us to go ahead and take the derivative. So g prime of x cubed, I apologize. G prime of x will now be the derivative of this, which is f prime, keep the inside the same, times it by the derivative of the outside, which is 6x to the 5th. So we can write it all as 6x to the 5th, f prime, x to the 6th plus 1. Okay, moving on, number 5. Use the graph of f to determine each of the following, where it's continuous. Okay, continuous has to satisfy 3 things. We need to know that the limit as x approaches a of f of x exists. We need to know that the limit, we need to know that f of a exists. And we need to know that the limit as x approaches a of f of x equals f of a. If this is true, then it's continuous. So let's look here. All the weird things are all in the graph of where we're really looking at. So -1. The limit exists, but the function does not. So it's continuous for everywhere except x equals -1. Anywhere else, let's look. The limit exists, the function exists, the limit exists, the function exists everywhere else. So this is the only place that it's discontinuous. Okay, how about differentiability? Differentiability exists everywhere except 3 things. Except cusps, corners, vertical tangents, or points of discontinuity. Okay, so differentiable except cusps, corners, vertical tangents, points, discontinuity. So here, let's start out with everything and eliminate what we need to. We already said that it's not continuous at -1, so because of points of discontinuity, it can't occur at -1. And everywhere else, we're looking for these other three things, the cusps, the corners, the vertical tangents. So right here, I would say that there is a corner at 0 because we're horizontal and we have a slope on the other side. So that's 0. Come down here, we have another corner that exists at 2, x equals 2. And over here at 3, something else going on. We've got a constant slope from one side and a slope of 0 from the other. Those aren't going to be the same. And that would be at 3. So these are the places where it's not differentiable. All right, moving on. For the values of x that make the function continuous or differentiable. Okay, so let's start out with continuous. Continuous, we want the limit as x approaches this value, 2 from the right, to equal the limit as x approaches 2 from the left. Okay, so let's look at this. These are x's that are less than 2, so that's from the left. So from the left, my function from the left, the function is approaching, let's plug in 2 squared minus 3, which is 4 minus 3, which is 1. And we need that to equal from the right, which is this part, which is 2 times a. So this will occur if a equals 1/2. 1/2. All right. Differentiability is really similar, except now with derivatives. We want the derivative, so the limit as x approaches 2 from the left of the derivative to equal the limit as x approaches 2 from the right of the derivative. So the difference here is we have to take a derivative. So let's look at the left over here. The left derivative is the derivative of this, which is 2x, which at 2 is really 2 times 2, or just 4. And from the right, with the derivative of a times x would actually just be a. All right, so here's a right here, and so this would be a equals 4. However, this is kind of a trick question. A function can only be differentiable if it's also continuous. That kind of references right up here. Points of discontinuity are a place where it's not differentiable. So we have to check, if a is 4, is this function continuous? So we have to check for continuity also. So let's check continuity. If a equals 4, from the left, the equation is going to look like 4 minus 3, or 1. And from the right, when x equals 2, the equation is going to look like a, which is 4, times x, which is 2. Does 1 equal 8? No. So therefore, there are no values that make this differentiable. No values make f of x differentiable. All right, let's move on to 7 really quickly. Suppose that f is continuous from -5 to 5. This is inclusive and has the following properties. The value at 0 is 2. So we're going to be actually graphing this. So at 0, f is 2. That's a point on the graph. At 3, the value is -2. Point on the graph. At 5, the value is 1. Now, this tells me how to connect these dots. This is the second derivative is negative from from -5 to 0. The second derivative is bigger than 0. It's positive. So this would mean concave up, right? From -5 to 0. And from -1.5 to 5, and from negative 1.5 to 5. So I want to draw something that looks like a cup from negative 1.5 to 5. It's decreasing when x is less than 3. So less than 3 on this side, it's decreasing. And it's increasing when it's bigger than 3. Okay, sketch a possible graph. Okay, we want to draw something that's concave up, and decreasing. We want to draw something that's concave up and decreasing from basically negative 5 to 3. I'm sorry, concave up and decreasing from negative 5 to 0. So let's look at our things. We've got, this is concave down. This is f double prime is negative. This is concave up. So this is f double prime is positive. So concave up and decreasing looks like this side. We want to draw that until we get to 0. It's still decreasing until 3, but if it's not concave up between 0 and 1.5, that means it has to be concave down. So this is decreasing and concave down until about 1.5. We don't actually know where the graph is. This is like an approximation. All right, now from 1.5 to 5, we're back to being concave up. So everything else is looking like a concave up, looking like a cup. We're still decreasing until we get to 3. So concave up and decreasing until we get to 3 is this half. And now we're still concave up, but that will mean that we are now increasing for bigger than 3. Okay, one thing I kind of messed off right here, these are closed brackets. So I put an arrow on the end here, but at negative 5, there really should actually just be a dot. And over here at 5, there's a dot, which makes it closed.